All right. Good evening, ladies and gentlemen. It's September 17th, 2021, 8:05 p.m. Welcome to this general meeting for the members of the Sacramento Valley Astronomical Society. It's our pleasure tonight to bring to you our very eminent speaker, Professor Raja GuhaThakurta, Professor of Astronomy and Astrophysics at UC Santa Cruz. The professor has a distinguished background. He received his bachelor's degree in physics at St. Xavier's College in Kolkata, India. He then came to America and received his PhD in astrophysics at Princeton. And he then worked briefly at the NASA Space Telescope Science Institute in Baltimore. He joined the faculty at UC Santa Cruz in 1994. He's currently a professor of astronomy and astrophysics there, and he works at the Lick Observatory, which I believe is under the jurisdiction of the UC Santa Cruz. And the professor's research concentrates on the formation and evolution of galaxies. And it is our pleasure to bring him to you tonight as our speaker. I'm going to mute everyone, no offense. Then I'll unmute the professor, and then he can give a talk. And he can share his screen as he wishes for his presentation. I will be muting you all in 3, 2, 1, and then Professor, feel free to unmute yourself and begin.
Now, can you hear me now? Good. Okay, thank you. Let me share my screen. Let's see if this works. I'm going to spend most of my talk time on this slide set that you're hopefully seeing now. I'm going to go into presentation mode. You should see a dark sky filled with galaxies, stars. Okay, I'll spend most of my time on this slide deck. I want to keep track of time so that I'm not running over. If I have time, I have a set of 4 slides that have to do with how this research relates to young people. And by young people, I mean elementary, middle, high school students, and how they're contributing to this research and how they're, how that's all working. So I can also save that for the Q&A. If someone asks a question about that, I can then bring up those slides. That might be the cleanest thing to do. So, because this part of the narrative is about people of a different sort, people that I've looked up to for my journey. So, all right. Thank you for inviting me. It's a real pleasure. I had, we had all hoped we could do this in person, but it's good that we're doing this anyway with Zoom. This talk is about the darkest secrets of the universe, and that's really a little bit of play on words because I'm going to talk about black holes, dark matter, dark energy. That's why it's about the darkest secrets of the universe. Those are some of the darkest secrets of the universe. So I've let the cat out of the bag, but that is a pun. So you'll see that in a moment. I've let Schrodinger's cat out of the bag. I will talk about Schrodinger's cat near the end of this talk. So that is a dark secret as well. So again, I'll talk about dark matter, dark energy, black holes, and quantum mechanics and the Schrodinger cat experiment. Not necessarily in that order, but strange as it seems, all of those things fit into the narrative that I'm going to present here. Even though the narrative is titled The Darkest Secrets of the Universe, it's very much about us humans, our place in the cosmos, and indeed even about our interaction with one another. Okay, so I'll talk about the process of science, which of course involves human beings, and as much as I'll talk about the people involvement of the process, but also about theory, experimental evidence, broader background, etc. Okay, so with that, I've been at UC Santa Cruz for 27 years now, and I've had the misfortune of being department chair for the last 2 of those years. And boy, those have been difficult years. These last 2 years have been about the most difficult time I've seen our department have in all of my 27 years. And it's a variety of things, right? Variety of external factors that have made all kinds of things difficult to do as a group. I had the good fortune of getting away from the UCSC campus to spend 8 months at Google about six years ago. And what I was doing there was they were helping me with the outreach work I do with high school students and now younger students as well. Okay. I'm going to talk about galaxies as you'd see. My research is on galaxies, but that's again central to the story. Just like atoms, like carbon atoms, hydrogen atoms, oxygen atoms, etc., are basic building blocks of matter, the matter that we surround ourselves with. They're basic building blocks of our bodies, of our homes, of our laptop screens. Atoms, I say, are basic building blocks. They're not the smallest because you do have protons and neutrons and electrons that are smaller than atoms. You have quarks that are smaller than protons and neutrons. But I think of atoms as basic building blocks because it's when our understanding of atoms reached a certain level of sophistication with quantum mechanics that represented some of the greatest progress in physics in human history. So atoms are, I feel, important building blocks, even if they're not the smallest or largest. And in the same way, even though galaxies are not the smallest nor largest building blocks, understanding them is sort of comparably important. Obviously stars are smaller than galaxies, and clusters of galaxies and superclusters of galaxies are much larger than individual galaxies. But galaxies are fundamental units of the universe in the same way that atoms are fundamental units of matter. And the simple reason for this can be summed up in one phrase. If we didn't live in a large galaxy like the Milky Way, we wouldn't have complex life here on Earth. We wouldn't have the atoms that form the basis of complex life on Earth. This is why galaxies are fundamental. The Sacramento Valley Astronomical Society would look very different if we lived in a small galaxy, or if we lived in a star that didn't have any other stars around it. That is, if we didn't live in a galaxy at all. And I'll hope to convince you of that in the next slide or two. Okay. So our place in the cosmos is very much within a galaxy. When I say our, you could imagine a picture of yourself or a picture of your family member. I imagine a picture of my son lounging on the carpet. There he is. And the story I'm about to say applies to canine life just as it does to human life. Here's an example of human life, sadly infected with, at least according to this inset, looks like this person's suffering from the coronavirus, because you have three life forms right there in this picture and inset. You have simple form, like a virus, and you have two complex forms, like humans and canines. You can have lots of things in between, of course. What is common to these life forms is the fact that they are based on complex molecules. And by complex molecules, I'm talking about proteins, DNA. The complexity of these molecules is directly related to the complexity of life on Earth. And by complexity of the way we look, complexity of how we function, and indeed the richness and diversity of life as well is related to this. Because if you wanted to build complex things out of very simple molecules, you'd only have a small number of permutations and combinations available. So you need these large molecules. This is a representation of a large protein molecule where every colored sphere represents a different atom in the periodic table. So red or orange and yellow and blue and green represent different elements in the periodic table. Now, to form these large molecules, you need to go deep into the periodic table. You can't just work with hydrogen and helium. Hydrogen is a one-armed atom. It has one electron with which to form a chemical bond. So it can form the end of a chain, but it can't be the central atom in any kind of complex molecule. It cannot, just has one chemical bond to form. Helium has two electrons, but it doesn't like to form bonds with anything. It's an inert atom. When you get to lithium, beryllium, boron, it's starting to get interesting. Carbon, nitrogen, oxygen, even more interesting. So we call ourselves carbon-based life for this reason. You need elements like carbon, nitrogen, oxygen to form complex elements. So our search for life really leads to these elements like C, N, and O. And of course, they're present in abundance on Earth. If you've been to a barbecue, you're wearing a diamond ring, you're carrying carbon on you, you're breathing nitrogen and oxygen all the time. So these elements are very common here on Earth, in the air, in the soil, in the oceans. It turns out these elements are also common in the sun. The sun contains essentially the same set of elements that the Earth does. So a natural question that astrophysicists asked many years ago is this: did the sun produce these large complex atoms? By large and complex, I mean significantly more complex than hydrogen and helium. Okay, so well into the periodic table. Did the sun produce these atoms, or at least did they produce the nuclei of these atoms through nuclear fusion? And the simple answer to this question is no. Even though the sun is undergoing fusion reactions, the only fusion it's doing is hydrogen to helium, nothing else. It's only fusing hydrogen to helium. Near the end of its life, it will produce other elements, including carbon, nitrogen, oxygen. It'll probably end its life as a carbon, nitrogen, or carbon, oxygen white dwarf. So it'll get up to sort of element 6, 7, 8 in the periodic table, atomic number 6, 7, 8 in the periodic table, but it hasn't done that yet. So what right does it have to have all these wonderful elements like iron, phosphorus, magnesium, manganese? What right does it have to contain those elements? What right does the Earth, do we have on Earth to enjoy these elements? And the right we have is sort of our right of ancestry. The sun, the solar system, all of its planets were born out of a cloud of gas and dust. And these large complex atoms that we're talking about, life-bearing atoms or important for life, were already present in the gas nebula when the sun collapsed under its own gravity and parts of it fragmented to form the planet. Parts of that cloud fragmented to form the planets we see in the solar system. So the elements we've been talking about, that we were on a search for, have led us to this notion of inheritance. We were born with these elements. Now, as scientists, we want to know how our ancestors acquired these resources, this wealth. And it turns out that the sun's ancestral stars, sort of like the stars in this picture, this is a star field in the Milky Way, but the sun's ancestral stars came in different temperatures, so different colors, different luminosities, different sizes. And this is a representative field of stars in our Milky Way. And some of the sun's ancestral stars were much more massive than the sun. And unlike the sun, because they're more massive and they have more intense gravity and they have higher temperatures, they're able to go through fusion reactions at a much higher rate than the sun. I'm talking about 1,000 times faster in the most extreme cases, certainly 100 times faster. So these massive stars, not only do they go through these fusion reactions very quickly, they get up to element 26 in the periodic table. So Fe, iron, is what it can get up to. These stars can get up to 10 times or 100 times, even 1,000 times faster than the sun. The other good thing about these massive stars is not only are they efficient cooks, much more efficient than the sun, versatile cooks, they can make 26 elements instead of the first 8. They're also very generous cooks. At the end of their lives, these massive stars explode. So everything they cook is returned to the environment. In this sense of generosity, these massive stars are our lifesavers. It's these things, it's the explosion of these massive stars that produced stardust. In fact, during the explosion, the rest of the elements of the periodic table can and are produced. Everything above number 26 can be produced through neutron bombardment, rapid neutron bombardment in the case of exploding stars. Now, the explosion is so powerful that it's really important that it be contained. If the explosion is too powerful, what would happen is the material, the star that produces these elements, explodes with such force, energy, gusto, that these elements completely run off into outer space, and the neighboring stars of the star that just exploded are left wanting. They're left wanting that stardust that their illustrious star just produced through its explosion. So you need a galaxy that has high enough dark matter content so that the explosion of supernovae don't escape the galaxy, they rain back in. And it's when it rains back in that you can have chemical evolution. The next generation of stars is born richer than the previous generation because they're enriched by the stardust produced during the life and death of the ancestral stars. In this sense, we had to be part of a big galaxy to be the way we are. Okay. If I stop my talk here, this is the essence of my story. Okay. What you see here is a picture of the Andromeda Galaxy. It's not a picture of the Milky Way. We can't take pictures like this of the Milky Way because we're stuck inside it and we don't have a long enough selfie stick to reach out and look back in on our galaxy. But if this were the Milky Way, we wouldn't live in downtown Milky Way. We wouldn't live out in the rural Milky Way. We live somewhere in suburbia, somewhere between the busiest area of the galaxy and the completely sparse areas of our galaxy. Again, if this had been a picture of the Milky Way, the sun and solar system would be in a perfectly ordinary place. The sun and solar system would be smaller than a single pixel on that image, so we wouldn't be able to see it. But it would be about 25,000 light years from the center of the Milky Way. The sun is located about 25,000 years of light travel time. So 25,000 light years is how long it takes light to travel from the center of the Milky Way to our solar system, or from our solar system to the center of the Milky Way, 25,000. And you can see from this picture that the diameter of this galaxy looks like it's about 4 times that, 100,000 light years perhaps. That's what we thought. That's what we thought was the size of the Andromeda Galaxy, 100,000 light years. Now, our group at Santa Cruz has been studying the Andromeda Galaxy for a long time. I started studying Andromeda nearly 30 years ago in the early 90s during the Clinton election. I still remember this. I was listening to the election news on the radio, freezing on a cold mountaintop in Tucson while we were taking images of Andromeda. And back then, everyone, including us, we thought that the Andromeda Galaxy size was about 100,000 light years across. What I've learned since that cold night in the early 90s, it took about a dozen years, but in 2005, we discovered that the Andromeda Galaxy is 5 times bigger than people previously thought. It's not 100,000 light years across, it's more like 500,000 light years across, 500,000 light years across. We started to find stars that are further and further and further away from the center of Andromeda, but they're moving with Andromeda. And they are not foreground stars, they're not background objects, they're at the distance of Andromeda and they're moving with Andromeda. So it makes sense to think that Andromeda is much bigger than people gave it credit for. Sorry about that. We and others have found that the Milky Way is comparably large. So large, in fact, that there may not be much empty space between galaxies. So this is a finding of the last 1 or 2 decades, is galaxies are big, really big. Now, Douglas Adams had told us that space is big, really big, but there isn't that much space between galaxies. So it's galaxies that are big and really big. I'll talk more about that in just a bit. Let me pause here for a moment and see if there are any questions so far. Anything at all about what you've heard?
Just a quick question. On that last point that you mentioned, that there may not be as much space between the galaxies, can you expand on that? I mean, visually, Milky Way and Andromeda look terribly far apart.
So when I'm talking about the boundary of a galaxy, it's not a physical boundary, of course. What happened? A good way to think about galaxies is you can see even from this image that it looks bright near the center and fainter in the outer part. So it's important to think in terms of number of stars per unit volume. So density of stars, star count density. And that density, if you plot that as a function of radius, it falls as you go to larger and larger radius. But it's a question of how rapidly it falls And does it ever cut off? And so far, we haven't seen a cutoff. It keeps going to a point where we can still detect stars that belong to Andromeda, detect stars that belong to Milky Way. Now, stars are very few and far between at that point. So it's very easy for galaxies to pass through each other. They can do that even in their central parts. Stars are so few and far between that galaxies, when they collide, they literally pass through each other. So that's what I mean. That's what I mean. And the difficult question to answer experimentally is when you see a star, you could ask the question, is it more attracted to us or another galaxy that's competing for its affection? And the way galaxies compete is through the force of gravity. So you really have to measure the motion of the object to understand not just where it is, how far away it is, but also how it's moving. Does that help, Professor?
That does. Thank you.
Okay, excellent. Other questions, please.
I was just kind of curious how you actually determine the size of them, of the galaxies.
Yeah, sort of that's how, right? So we're plotting density as a function of distance from the center. So in the case of Andromeda, we know how far away it is. So its angular distance translates to a physical distance. In the case of the Milky Way, it's a little harder because we have to measure how far away the star is from us. And that tells us how far away it is from the center of the Milky Way, because we know the distance between us and the center of the Milky Way. But in all of these cases, you need to know the distance of the star from the center of the galaxy. So you can make a plot of density of stars as a function of distance from the center. And in such plots, the density doesn't drop to zero. It keeps going. It keeps going at a detectable level where you can actually detect stars with telescopes. You can isolate stars, identify them, secure their membership, whether it belongs to this galaxy or that. That's really what I mean by mapping the size. Okay. Thanks for asking this. This is great. Okay. We can take pictures of the Milky Way just from the inside. And this, I wanted to show this picture because this is, you see a picture of the Milky Way here that's more or less horizontal across the bottom. And what I'm going to show you is a time-lapse movie put together by John Rockman, my friend here, who teaches physics in Palo Alto. He took this from a game park in Kenya. He took a set of pictures with a digital SLR, stitched them together into a time lapse. So I'll remove the label so it doesn't distract you from the movie, but I'll play the movie a couple of times. And what you're seeing is the apparent rotation of the Earth that makes it look as though the Milky Way is sweeping across the sky. There's all kinds of cool things going on here. There's clouds, there's lightning, there's shooting stars. There's of course the Earth's rotation that you're seeing in reflex when you look at the Milky Way. I'll play this one more time. You'll see trees fluttering in the breeze early on. This is close to sunset. It will soon get darker. You'll see the sky is getting darker now. In the Milky Way, it becomes more prominent. So this is about a 4 or 5 hour time lapse. You can see the Milky Way starts nearly horizontal and ends up nearly vertical. Horizontal to vertical would be 6 hours because 4 times that would be a full circle. So anyway, it's a remarkable movie. Now, I have another remarkable Milky Way time lapse to show you. For the second one, this is not taken by John Rockman, it's taken by somebody else. It's taken by Art. What's the last name? Let's see if I have the name here. Oh, Arya Narenberg has taken this. Okay, now what this photographer has done is, because we know the Earth's rotation is going to make the Milky Way swing around, they've set up their camera in such a way that it tracks the rotation of the Earth. So as the Earth rotates, the camera rotates. And something remarkable happens when you do that, right? So this is wild because, you see the rotation of the Earth essentially in a way that I've never seen so explicitly, because, the camera is rotating exactly to keep the Milky Way fixed. And you have no choice, therefore, than to let the Earth swing around in the camera's field of view. So this is really spectacular. I think this is this should be shown to the flat earthers and those who doubt that the Earth is spinning, right? I mean, I'm sure I wouldn't be able to convince them still, but it's really remarkable. Okay. Now, I said I would talk about people a little bit, and one of my favorite people in thinking about astronomy is Immanuel Kant, a philosopher. Back then, when there was very little known about the universe, most of what we call science today was philosophy, because you could make theories, but you couldn't really test them. And Kant was a really, really smart cookie. And he was born in what is now called Kaliningrad in Russia, but it was called Prussia then, Königsberg. Lived to the age of 80, which was not common then. And even posted a selfie at the age of 31, which is what you see here. And sort of came up with this notion that these fuzzy things of light, we call them island universes. Island universe. This term is attributed to Kant. He was quick to deflect this term onto others. He said, no, these phrases came from Thomas Wright and Sir William Herschel. But most people attribute island universe to Kant. And what Kant is talking about here is he imagined that the universe is made up of islands, just like, let's say you go to the Hawaiian island chain, these land masses are separated by vast amounts of ocean in between. You can see where I'm going with this. What we are finding is the oceans, as we dig deeper and deeper and deeper, there's not that much ocean. These islands are practically connected. So Kant's notion of island universes is exactly what we're trying to address here with our studies. Now, really remarkable. To think that this was done 250 years ago is absolutely remarkable. More than 250 years ago, 1755. Now, apparently Kant never left Königsberg. He didn't travel throughout the world, nothing. And he had this view that was not just global, but really had a view of the universe. The story goes that he applied for a faculty position in the philosophy department at the University of Königsberg. And apparently the university turned him down. Just think about it. There's no one more famous from this town. I bet you haven't heard of anyone more famous than Immanuel Kant from Königsberg or Kaliningrad. And they really blew it. The first time he applied for a job, they turned him down. Fortunately, apparently he applied a second time and they gave him a faculty position. So my faculty colleagues and I have this running thread of what it takes to get a faculty position. I'm sitting pretty with a faculty position at Santa Cruz and feel guilty that someone as smart as Kant didn't get a faculty position first time around. And, so arguments are made that, money was scarce. And when you hire a faculty person, even true now, you have to pay their salary. And with the tenure system, you're paying their salary indefinitely. In modern day faculty positions, it's even more expensive because you have to pay for my toys. If I get hired by a university, you have to pay for my telescope. You have to pay me to get access to Hubble, Keck, whatever. Now, if you hire a theoretical physicist, the toys they need are a desk, a chair, a notepad, a pencil, an eraser, and a wastebasket. If you hire a philosopher, you don't even need the wastebasket. They're going to keep everything they write. So anyway, this is idle speculation on our part, as you can see. But Kant's notion of the island universe was a really powerful thing, and yet it died a natural death, and people forgot about it for about a good 150 years. And in the early part of the 20th century, 1905, 1906, there was another raging debate. In Kant's time, there was no debate. This time, there was a debate. Enter Harvard's Harlow Shapley, this picture you see here, and someone named Curtis. Curtis and Shapley had this debate, 1906, I think. Shapley argued that the Milky Way is huge, and these things that Kant call island universes and other people call nebulae because they look like clouds of light. Shapley said, oh, they're all inside the Milky Way. The Milky Way is huge. These things are nearby. They're inside the home we live in. In other words, he thought of the Milky Way as our universe. It's everything. And Curtis had a diametrically opposite view. He said, no, the Milky Way is relatively small, just like those island universes that we see. They're actually outside the Milky Way. They're just like the Milky Way, but they're so far away that they look like tiny fuzzballs of light. Curtis was right. Shapley was wrong. Indeed, those things that Kant called island universes and Shapley and Curtis called nebulae, they're indeed entire galaxies like the Milky Way. Time magazine blew it and put the wrong person on the cover, right? They put the loser of the debate on the cover. And they weren't going to put another astronomer on the cover just to make up, because they hardly put astronomers on covers of Time magazine. So instead, what they did was, in fact, if you look at this Time magazine cover, it says Harvard's Harlow Shapley at the right below his picture. I don't know if you can see that on my Zoom screen share, but it says Harvard's Harlow Shapley. Now, this is volume number 26. Now, apparently, a few months later, we're talking about a different volume of Time. Let's see, this is also 26, but instead of number 3, this is number 8. So 5 volumes later, 5 months later, I believe, they published this other cover. And instead of putting Curtis on the cover, they did a more typical thing of putting a Hollywood star on the cover. Now, what is interesting is her name is Jean Harlow. Her last name is the same as Harlow Shapley's first name. And apparently, and I never got a chance to check this, but according to my physics professor in grad school, he said that inside the magazine, they referred to Jean Harlow as the Shapley Harlow. And this was a direct play on words. They were basically poking fun at themselves for putting the wrong person on the cover. And they went through this elaborate shenanigan of putting Jean Harlow on the cover and referring to her as the Shapley Harlow. Why my astro professor knew this beats me, but he had all these utterly useless facts up his sleeve. Entertaining, but useless. All right. Now, my love affair with galaxies started, as I said, about 30 years ago. I was in Tucson taking pictures of the Andromeda Galaxy. Here are the 4 pictures I took of Andromeda back then. It's actually not 4 pictures. One way of looking at it, it's really 1 picture. Another way of looking at it is it's 57 pictures. Let me explain. There are 4 panels here. Each panel is the same digital data, just shown at different contrast levels. Okay, so low contrast, lowest contrast on the left, highest contrast on the right. You can see the Andromeda Galaxy. You can see its companion. This companion is called Messier 32. This one here is called NGC 205. You can see it sort of peeking out on the left. It's the same image at 4 different contrast levels. Why do I say 57 images? Because each of these images is a digital mosaic of 57 frames, some in blue light, some in infrared light. That's why you see this sort of scalloped edge all around. And look, we thought we were done. He said, we've taken this image of Andromeda. We want to measure how bright it is. And we felt, we've probably gone out as far as we need to go out to capture all of its light. And boy, were we wrong, because this goes out to about a diameter of 100,000 light years. Like I say, we later found out that it goes out 5 times further than this. So, but I completely fell in love with galaxies and with Andromeda when I first took this picture. It really felt like we were coming in for a landing. This galaxy looks so spectacular on our digital images. So here they are. I had a couple of PhD students, well, 1 PhD student and 1 undergraduate who worked on stitching this mosaic together. This was the first digital mosaic of Andromeda. People had taken photographic images of Andromeda at that time, and they had taken single digital frames. But the whole notion of, today you can take your iPhone and sweep it across in panorama mode, and it'll instantly stitch things together. But to create a distortion-free mosaic is not easy. And so our students, Andreas and Phil, went through a lot of pains to make this mosaic. And I took the original images with Shomo Krai-Chaudhuri. So the 2 of us took the images, and Andreas and Phil separately did the hard work of stitching things together. Okay, here's a more modern image, single digital SLR image now, wide field. This is taken by Robert Gendler, who's a famous astrophotographer. He's a doctor by day in Connecticut and an astrophotographer by night. And you can see the 2 companions of Andromeda, M32 here and NGC 205. And what our group at Santa Cruz does now is we use the telescopes on the summit of Mauna Kea. They're just showing up here in this sort of beautiful Hawaiian sunset. On the sacred summit of Mauna Kea are two of the most powerful ground-based telescopes, the Keck telescopes. They are 10 meters across. The mirror is 10 meters in diameter. It's not a single mirror. It's 36 segments, each the size of a tall human being. So these are spectacular telescopes. And in fact, earlier this week, Monday, Sunday night, Monday morning, I was using the telescope in Hawaii. I'd gone to Hawaii after 18 months of being, under isolation because of COVID-19. I finally went back to Hawaii and I was on the telescope for 9 different nights. And it was spectacular, spectacular. I didn't go up to the summit. Actually, we operate the telescopes from the headquarters of the observatory, but it was just stunning. The skies were fantastic. The telescope performance was fantastic. And we were studying a companion of the Andromeda Galaxy on those nights. We were trying to measure how fast stars move, but trying to map the extent of the Triangulum Galaxy, which is not far from Andromeda. Okay, so I used the Keck telescopes to study the extent, the dynamics, the dark matter content of Andromeda, its star formation history, its age, its chemical enrichment history, all of these things. Now, in addition to these telescopes on Mauna Kea, we use the Hubble Space Telescope. And there's a cartoon of it in the lower left. The Hubble telescope was used by our team over a 4-year period to map the white outlined section of Andromeda. It's like a crime scene outline. You draw with the chalk, you draw on the floor. Within this outline, Hubble took a modern mosaic. Remember, we had taken this mosaic in 1992 of 57 frames. Well, Hubble took 3,000 frames, not 57, 3,000 frames, not just in blue and infrared light, but in 6 filters, 2 ultraviolet filters, 2 visible light filters, and 2 near infrared filters. And it produced this spectacular image of that crime scene outline. The details of that, 117 million stars were identified in that image. The PI of this project was a good friend of mine, Julian Del Canton. Our Santa Cruz group is very much part of this project. In my next slide, I want to show you some of the details of that Hubble image. Now, before I go there, though, I want to emphasize that Andromeda is very big on the sky. It's just low contrast. That's why you can't see its details. It's much bigger than the full moon in terms of its angular extent. You can see the full moon to scale in this picture. It's huge on the sky, but it's just very low contrast. So our eyes can't pick it up. You need binoculars, or better still, you need a digital image so then you can crank up the contrast. Our eyes get too saturated. Our eyes are logarithmic devices and they get too saturated. They're not able to see anything like this detail. Okay, so I promised I'd show you the details of that Hubble image. Now, there's Andromeda, this little ellipse down here. This is the arc of the Milky Way, gas and dust in the Milky Way. And what we're going to do is we're going to zoom in to the Hubble image mosaic of Andromeda. So I'll remove the label so you can focus on the image. And again, this is the arc. This is the great circle of dust and gas. That's the Milky Way. But we're going to zoom in. So fasten your seatbelts. We're going to zoom in a long way. You can see the details of the Andromeda Galaxy a little better now. You can see the 2 companions, in fact. And we're going to keep zooming. This is not a made-up computer animation simulation. This is the actual Hubble image of Andromeda that you're seeing here. No, you're not pulling any punches. This is how it is. Okay, this is the colors are created by taking images in different filters. So if our eye was sensitive enough, it would see this range of colors. You'd see red stars, you'd see blue stars, you'd see patches of darkness, like you see up in the upper left here. These patches of darkness are clouds of gas and dust blocking the light of stars. This looks remarkably like the star field we saw in our own Milky Way. So Andromeda's contents are very much like ours. If Kant had images like this, or if Curtis and Shapley had images like this, they would see immediately that these distant fuzzy things, if you look in enough detail, they're just like our own galaxy. So this is one of my favorite portraits. I'm an artist and I love drawing portraits of people, but this is one of my favorite astro portraits of a galaxy. This is really looking at the tiniest details on the face of Andromeda. Here's a good way to think of this image. the next time you're on your flight going somewhere, let's say you're coming into land and the plane banks as it's coming into the airport, it tilts, so you're sitting in the window seat and you can look straight down, and you're flying over Santa Cruz Beach, say. You're flying over some beach, let's say Santa Cruz Beach. You take out your cell phone and you take a picture of the beach below you. Imagine your cell phone has such high resolution that if you zoom in with a reverse pinch, you can see the individual grains of sand. That's what this image is. It's like taking a picture of Andromeda with high enough resolution so you can see the whole beach, but you can also see the individual grains of sand. We're talking about 117 million stars, so I'm not exaggerating when I say that. Okay. Let me pause here one more time to see if there are any questions, and I'm also going to do a quick time check. Okay. Any questions? Yeah.
Professor, we did have a audience member in our chat room ask the question, why are there two telescopes? They're both 10 meters. Why are they side by side? Is one optical, one infrared? Why have two identical side by side?
There are a couple of answers to that. The main thing is when you build one, a lot of work, a lot of expense and work goes into designing, mechanical engineering. It's much cheaper to build a second copy. It's much harder to build something that's different. Now, when you build two telescopes, if they're not talking to each other, they're just looking at different patches of sky, you can have twice as many people using it. Now, the Keck telescopes are shared by the entire University of California system, the entire Caltech system, the community of NASA astronomers. There are many communities sharing them. We wish we had 10, not 2. So there's not enough time to go around compared to the demand. So that's a simple answer, that it's cheaper to build clones once you've figured out all the mechanical challenges. There's a second reason. You can indeed, as you said, you can optimize the two mirrors. So a telescope only is good for focusing light. What you do with that light is put it into a spectrograph or camera, and you can look at infrared light, you can look at ultraviolet light, you can look at optical light, and the different telescopes are optimized differently. The mirror coatings are optimized differently. They have different instruments that the focused light goes into. We don't swap instruments between the two telescopes unless we absolutely have to. Each telescope comes with a suite of cameras and spectrographs that's distinct from the other telescope suite. Finally, one of the things that's been done a little bit, not a lot, is you can combine the signals from the two telescopes. And you can use it in, like you use a radio interferometer, and you can use it as a telescope that's 100 meters in size instead of 10 meters, because the distance between the two telescopes is 100 meters. So Keck interferometry has been done in a limited way. It's very difficult to do, but you have a baseline where you can, where just from, not from a light collecting power standpoint, but from a sharpness of vision standpoint, the two telescopes together can behave like a 100-meter telescope. That's a great question. I hope I've answered it.
Thank you, Professor.
I'm looking at the other chats. Okay. That was the only question. Yeah, this is not noise. These are all stars. This section is about as far out from the Andromeda Galaxy, a little bit further out from the center of the Andromeda Galaxy, as our sun and solar system are from the center of our Milky Way. So we are 25,000 light years away. This may be 30, 35,000 light years from the center of Andromeda. Perfectly average place. Now, these stars look like they're very close together. They're not. There's a lot of empty space between stars. Why do they look like they're close together? A, because there's a lot of depth. So even though two stars look like they're close together on the image, one is in front of the other. Second, what you're seeing here as a blob is not the true size of the star. Hubble, in spite of its eagle vision, has finite resolution. So if Hubble had even better resolution, the stars would look more point-like. So the apparent sizes that you see here of each star is not real. It has to do with finite focus of the telescope. Okay? All right, let me move. Yeah, sorry, go ahead, please.
No, thank you.
Okay, thank you. All right. Now, I said that in 2005 we found Andromeda is big, really big. Five times bigger than we previously thought. Now, imagine you wake up one morning and you find you're 5 times bigger than you were. You're going to bump into things, right? You're going to bump into things, or you were bumping into things all along and you didn't know it. That's more accurate. So that's exactly what's going on with Andromeda. Andromeda is so big that it has been bumping into things, cannibalizing things to an extent that we hadn't realized. The Milky Way is big, Andromeda is big. In 2012, I was part of a group led by a group in Baltimore, where I worked briefly, where we tried to make the measurement of the 3D motion of Andromeda. Every velocity has 3 components, x, y, and z. The z component of Andromeda, which is the component to and from motion, towards us, away from us, that's been known for 100 years. That's Andromeda's z component is towards us. Now, if its x and y components are 0, then the galaxy is moving towards us. But if its x and y component are as big as the z component or bigger, then the galaxy is moving at some tangent. It's not going to collide with us. So in 2012, after much painstaking work, by taking repeat images with Hubble and seeing how stars and Andromeda move between repeat images 5, 6, 8 years apart, we finally figured out that the stars in Andromeda are hardly moving across at all. In other words, their Vx and Vy are really close to 0. Vz is all it has, and all it has is us in its sight. It's moving towards us. We discovered this in 2012. So you found that your neighbor is 5 times bigger than you thought it was and coming right for you. What this means is there's a collision in our future. So I want to show you in this slide what galaxy collisions look like. Galaxy collisions take a long time to unfold, billions of years to unfold, but we can speed them up on a computer. And I want to show you computer simulations compared to actual snapshots of colliding galaxies. So again, I'll remove the labels so you can focus on the visuals. And oh, is my screen blank right now? No, right? It was temporarily.
It's working. It's working now.
Okay. Oh, good. Yeah, no, that was meant to be blank. Sorry. Yeah, I just got your chat. Thank you. No. Okay, so I'm going to remove the label, and here are 2 computer galaxies, computer models of galaxies, and as they come together, we stop the computer simulation. And here is a real picture of 2 galaxies that are about to collide. Okay, real picture, this one. We go back to the computer simulation. The mutual gravity is all built into this computer simulation, n-body simulations, the gravity of n particles acting on every other particle. And again, the galaxies are intersecting. We stop the computer simulation, change our perspective, stop. Here's a real pair of galaxies intersecting, actually passing through each other. We go back to our computer simulation. Galaxies start to stretch each other out. Now the near end is pulling, the near end is being pulled harder than the far end. This is a real pair of galaxies that are being stretched out, this third pair right there. We go back to the computer simulation. The central parts are about to fall back together. We stop our computer simulation right there, change our perspective. And here's a real pair of galaxies further along in the collision process. So galaxies collide, but they take a long time. So if you only have snapshots, we have to somehow stitch them together through computer simulation. Then that's exactly what this simulation has done. This is the final snapshot, very late stage, where the central bodies of the galaxies have merged, but these long tails remain. Now, when the centers of galaxies merge, of course, the big black holes at their centers merge. The result is this big old elliptical galaxy. So that's what you're about to see next. But one such elliptical galaxy is going to be formed by the Milky Way Andromeda collision. So this is now a different kind of movie showing you what we anticipate the future of our sky to look, the future sky, because as you know, Andromeda looks very small in the sky, very small in the sky. And I remember when my daughter was playing softball, she told me this joke. She said, Jenna wondered why the softball, was getting bigger and bigger, and then it hit her. So this is what astronomers say about Andromeda. You know, astronomers wondered why Andromeda was getting bigger and bigger, then it hit us. that's what's supposed to happen, right? So again, I'm going to remove the label. And this is a little bit of fantasy because we don't know exactly what the future looks like. But today, Andromeda looks small and insignificant. But in a couple billion years, it's going to be a lot bigger. And in about 4 billion years, there'll be a spectacular collision between the two galaxies. And they will destroy each other's beautiful spiral morphology, spiral form. And they will, in fact, produce a big old swarm of stars called an elliptical galaxy. So this is far in the future, 7 billion years in the future. That's a typical time scale for galaxies to collide. But this is what's in our far future, if we survive long enough to see it, right? Many other bad things will happen. You know, we'll have other politicians who'll bring us to the brink of death. We'll have the sun. Well, we'll have the environment to contend with, disease. If we survive all those things, the sun is going to bloat up into a red giant and gobble us all. So to see this, to see the Andromeda Milky Way collision, we have to escape from our location in the solar system. We have to move outwards to one of the moons of Jupiter and Saturn. And from the comfort of our living room couch there, the astronomical living room couch, not too close to the fireplace, we should be able to watch this, right? We have a few billion years to figure out the technology. When I say we, I mean that in a figurative sense. It's not going to be me. Okay, now, so when big galaxies collide, you get elliptical galaxies, and I'm going to skip this particular movie in the interest of time. Sorry. Here's a big elliptical galaxy in the Virgo cluster called Messier 87, and as we can see, there's a supermassive black hole at its center. The heart of the M87 galaxy is dark. Okay, it's got a black hole. These galaxy collisions, by the way, are moderated by dark matter. That's what we're trying to understand when we study galaxy collisions, is the distribution and amount of dark matter in galaxies. This is a picture of this elliptical. At its heart is a supermassive black hole. So I'm going to play this movie just to zoom in. And as we zoom in, you'll see that the ground-based telescope doesn't have any more resolution. We don't see any more detail. So we have to resort to physics models to see what's going on near the center. So what you're about to see is a model of what we think is going on near the center. And then in this model, you have swirling material around a black hole. And that's what we think produces this jet of material. That's what we think heats up through friction to produce X-rays and very energetic light. Now, this very black hole at the center was the subject of a portrait. This was a very famous portrait of a black hole, the silhouette of a black hole. It's that very black hole at the center of that very galaxy, whose background radio emission is bent by its own gravity to produce this Einstein ring. Now, this is a remarkable picture taken with not one radio telescope, but a slew of radio telescopes scattered around the Earth, so that it's working like a telescope that's the size of the Earth. Just like I said, for the Keck telescope, the two telescopes work like a 100-meter telescope. If you have enough radio telescopes scattered around the world, they behave like they have the sharpness of vision of a telescope that's the size of the Earth. Okay, so that's what was used. It's called the Event Horizon Telescope. It's an array. It's not a single telescope. It's an array of telescopes. Now, quite a remarkable image. This came out a few years before the pandemic, not very long before the pandemic. Now, but that bending of light is remarkable, predicted by Einstein. Light should be bent by gravity. Before that, Newton's light traveled straight. Einstein's gravity says, don't think of gravity like an invisible force, but think of gravity as distorting space and time in its vicinity. Any object with mass distorts space and time in its vicinity, and literally everything that goes through that space-time has to bend, whether it's light, whether it's massless. Light has no rest mass. Whether it's massless or has mass, anything that goes to, it's the warping of space-time that's causing it to bend, not any mysterious force. So in Einstein gravity, in general relativity, you have bending of starlight by the sun in a solar eclipse. You have bending of starlight in that event horizon image, and you have wonderful images like this, the smiley face image, where the background light of these blue galaxies has been stretched out into parts of Einstein rings, arcs, by the two eyes, the galaxies that form the two eyes of this happy face. It's their gravity that's doing the bending of light. This is quite remarkable, really quite remarkable. And this really, credit goes to Albert Einstein on the picture on the left there. This is a photo taken in 1912. And on the right is a very famous friend of Albert Einstein's, Carl Schwarzschild, contemporary of Einstein. And Carl was a very good mathematician. He was the first one to solve Einstein's equations of general relativity in exact form. He solved it for a point mass, okay? Simplest case. 1912 was a special year for Carl Schwarzschild too, because he and his wife gave birth to, they had their first son. Martin Schwarzschild was born in 1912. Now, Carl Schwarzschild died shortly after the birth of his son. He died in World War I. Brilliant man. He was in his 30s when he had solved Einstein's equations. Hugely famous person already by his mid-30s. And he was fighting for Germany in World War I. Ironically, he gave his life for Germany, as you might imagine from the name, Carl Schwarzschild. Schwarzschild is a Jewish name. Schwarzschild died in World War I, not from battle shot, not from battle wounds, but because the conditions were so unsanitary on the battlefront. So at his untimely death, Einstein lost one of his closest friends and would go visit Carl Schwarzschild's widow and his son Martin. Okay, so Martin remembers Einstein coming to their home when he was a little boy. Martin got very angry, as rightfully, with the Nazi party, because his father had given his life for the country. Now they were being persecuted as German Jews. So he and his mom and siblings came away to the US. He went and he enlisted in the US military so he could fight the Axis powers. So what happened there was the Schwarzschild became a professor at Princeton. When I joined as a grad student, he had already retired, but he became one of my mentors. And I tell this story because Martin is my 1 degree of separation from Albert Einstein. He knew Albert Einstein when Martin was a child, and Einstein would come to their home. Now, going to a place like Princeton, I knew there were other senior professors like Lyman Spitzer and John Wheeler and Freeman Dyson, who knew Einstein in a different context. Einstein came as a professor to the Institute for Advanced Study. So they were also 1 degree of separation for me to Einstein. So I had 4 1 degrees of separation to Einstein, one of whom knew Einstein both in Germany and in Princeton, and the other 3 knew him only in Princeton. This is why the people part of the story is super important to me, because as I think back on my career, it's these individuals who have been absolutely remarkable. To think of how bright and amazingly smart they were, and to have even shared any kind of experience with them is remarkable. Here's another person I had the good fortune of listening to a talk from, Stephen Hawking. This was, as you know, he passed away a few years ago, but another remarkable person who helped us understand black holes. I went with a friend to listen to his talk in Santa Clara. Here are 3 other role models of mine. You may recognize one of them, the one on the right. I had the good fortune of meeting Mother Teresa for 30 seconds in Calcutta in 1985. The person in the middle is Chandrasekhar, who really is considered one of the first people to understand that stars can collapse into something like black holes. One of Chandrasekhar's thesis students was Guido Munk. Guido Munk's thesis, one of his thesis students was Jim Gunn, and I was Jim Gunn's PhD student. So Chandrasekhar is my my great-grand doctoral advisor. You have scientific genealogy just like you have biological genealogy. And the person in the far left, Vera Rubin, is the discoverer of dark matter on galaxy scale. So I've had the good fortune of meeting all 3 of them, but I put them up here because they've been my inspiration, absolutely my inspiration. All right, I'm looking at the time, and I'm going to keep going. One of the other predictions Einstein made was that if you have the merger between 2 neutron stars or black holes, well, there were no neutron stars in Einstein's lexicon, but if you had a merger between 2 compact objects, you could send ripples out through space and time at the speed of light, and these are called gravitational waves. Einstein predicted these in 1915. It took 100 years, 2015, for the Laser Interferometric Gravitational Observatory, LIGO, to detect these things. So it's a remarkable story. It's a remarkable story of what you can achieve through hard work, self-belief, and precision. And I think of this person when I think of what you can achieve through hard work, self-belief, and precision. Steph Curry. What Steph Curry is to all his sports, not just basketball. He's inspired people to watch who are not even interested in sports, just like Federer and Serena Williams. There are people who elevate things beyond themselves, beyond the sport they're in. The gravity wave detection was like that. It elevated gravitational physics, elevated all of science. People who were never interested in these things got interested because it's such a remarkable feat to see it. So this is the schematic of the apparatus. I won't go into the details of this. If you ask me, I can later. This is what it looks like from the air. It's L-shaped. Each of the arms of the L is 4 kilometers. And when a gravity wave goes by, one of those arms of the L gets longer than the other temporarily. It goes through oscillations. If you think about the amplitude of the oscillation, that is how much is the 4 kilometers changing by, it's something ridiculous. The change in length divided by the original length is 10 to the power minus 21. Okay, right. Let me explain what that is. If you take 4 kilometers and you multiply that by 10 to the minus 21, you get a number that's 1/100th the size of a proton. Okay, you take 10 to the minus 21 multiplied by 4 kilometers, you get a length that's 1/100th the diameter of a proton. How can you measure this? Well, you can measure this because the way this is set up is you make light interfere destructively so that you're not seeing any light at all, because the crest of one of the bounces and the troughs from one of the other bounces coincide. When the two arms are at exactly 4 kilometers, you set it up like that. And when a gravity wave comes by, that intensity goes up and down in rhythmic fashion. That's what you're seeing here. Okay. And the y-axis is literally measuring delta L over L, change in length over the original length. The lower graphs are what you would expect when two black holes merge. The upper graphs are what was seen. It doesn't take a rocket scientist to see that this is a remarkable detection. You'll see two things. You'll see that the waves get bigger, deeper in amplitude, bigger in amplitude, right, as you go forward in time. But you also see that the frequency gets higher, they get more rapid. That is if you imagine the x-axis to be time and the y-axis to be amplitude, amplitude grows and the frequency grows too. This is exactly what would happen when two black holes start spiraling in. They lose energy because they're losing energy through gravity waves. But as they get closer and closer together, the gravitational field gets more intense. That's why the amplitude goes up. But their orbit gets faster and faster. That's why the time axis shrinks. So again, lower axis is what you expect to see. Upper axis is what was actually seen. This was the first detection by humanity 100 years after Einstein's prediction of the merger of two black holes and the gravity waves they produced. A few years later, again, 1/100th the diameter of a proton for a 4 kilometer array. Absolutely remarkable feat of engineering physics. A couple of years later, 2017, two neutron stars merged. And this time, unlike black holes, when neutron stars merge, there's a burst of light. And that's that burst of light that you see a red arrow pointed to it. That flash wasn't there before. That point of light wasn't there before the gravity waves were detected. So now, not only have we heard the chirp in the forest, in what used to be a silent forest, not only have we seen the chirp, we've seen the culprit. We've seen the birds that caused the chirp because we saw them fly away. So it's quite remarkable. We live in a very, very exciting era. Please tell me how I'm doing for time. I had budgeted 75 minutes for my talk. We're at 9:09. I can't remember if we didn't start exactly at 8, but I do want to be done with my talk at 9:15, if that's okay. Is that all right?
That's fine, Professor. You have as much time or as little time as you would like. You've been talking for just over 1 hour.
Okay, good to know.
So we
I
leave
was
it to
trying-
your discretion as to how much time you want to take and how much time you want for Q&A. It's up to you.
I'll take a little bit more time to finish my story, and then I'll take Q&A. Okay, so where did the Milky Way come from? Because the reason I asked this question is I hope I convinced you at the beginning, long before we got into Einstein and Schwarzschild and Hawking and Mother Teresa and Vera Rubin and Chandrasekhar. In my second or third slide, I tried to convince you that we wouldn't be here if we didn't live in a galaxy. If you were convinced by that, you have to then ask the question, how did galaxies form? Because that's the next question to ask if we want to understand our origin. It's not enough to say we needed a big galaxy to get here, but how did the big galaxy get to be the way it is? So where did the Milky Way and other galaxies come from? And the answer takes us all the way back to the earliest moment in the universe's history. So for this question, I have to go to Schrodinger's cat. Okay, Schrodinger's cat is a thought experiment, a Gedanken experiment that Schrodinger never carried out. And in this experiment, Schrodinger questions the quantum nature of microscopic physics. So, if you have anything that's microscopic, it's said to be fuzzy on small scales. Now, Heisenberg uncertainty principle, Schrodinger's cat, you can't predict the position and momentum of a particle with arbitrary precision, is what the uncertainty principle says. So in other words, if you set up a bunch of radioactive material, as you see in that cartoon, you can tell statistically that every hour maybe one alpha particle is emitted, every hour one is emitted, but you can't tell. You can only say that in a probabilistic sense. In other words, if you set up 1,000 boxes, and let's say there's a 50% chance that in an hour an alpha particle is emitted. If you set up 1,000 boxes like this, in about 500 of them, there'll be an alpha particle emitted in, and you wait for an hour for all 1,000 boxes, there'll be about 500 of them, there'll be an alpha particle. The other 500, there won't. That's how probability works. You can't predict which of the boxes, but you can predict the number, but you can't predict which boxes. So inside the box, Schrodinger thought experiment, not actual, puts a cat, a live cat, and he sets up the alpha particle to go and strike a Geiger counter. Now, Geiger counters normally beep, but in Schrodinger's cat experiment, instead of beeping, a hammer falls on a bottle of cyanide that's lethal to the cat. So if you open these 1,000 boxes an hour later, 500 of your cats are going to be alive and 500 are going to be dead, but you can't predict which before. So this is the dead or alive question. Wanted, I have a poster that says wanted dead or alive, Schrodinger's cat. Wanted dead and alive in this case, because Schrodinger went on to say that the cat is a superposition of a dead state and an alive state, 50-50 superposition in that situation. Alive or dead. Now, Schrodinger was an animal lover and never carried out this experiment. However, nature, the universe, went ahead and did its own version of the Schrodinger cat experiment. And the way it did it was the following. Shortly after the Big Bang, this is time on the x-axis, shortly after the Big Bang, there were quantum fluctuations. Just like the Geiger counter takes that microscopic alpha particle and moves it in the macroscopic domain by beeping or having a hammer fall, there's something called inflation, which is very rapid expansion of the universe shortly after the Big Bang. It's that caused the universe to go from its microscopic fluctuations to turning those into macroscopic things. So these tiny fluctuations, if it were an up fluctuation, it became a galaxy. If it was a down fluctuation, down in density, it would empty out and there'd be a void between galaxies. So we are living in nature's version of the Schrodinger cat experiment. Our Milky Way galaxy is a live cat. The gap between us and Andromeda is a dead cat, is one way of looking at it. Okay, now, how do we know there were quantum fluctuations after the Big Bang? We can see that in the afterglow from the Big Bang. And this is the next picture I want to show you. This thing that looks like modern art is actually a map of the sky. You're seeing the afterglow from the Big Bang. These are the early ripples in the cosmic ocean. This is an actual map for which a Nobel Prize was given out to measure the afterglow from the Big Bang and the ripples on the face of the universe. So you take these tiny fluctuations, and if you give it enough time, what happens is These tiny fluctuations grow under gravity. They get amplified by gravity, and they turn into this giant cosmic web. If you're wondering about the unit here, kpc, 1 kpc is 3,260 light years. 1 kpc is 3,260 light years. That bar is 500 kpc. This is about the size of a, small group of galaxies, bigger than a single galaxy. The simulation is set to music, actually, and I'm listening to the music, but I'm not playing it for you. Because there's no music in space. It's all vacuum. This is a spectacular simulation. One of the things this says is our advances in understanding the universe and cosmology have come from telescopes. But they've also come from supercomputers, being able to do these calculations, run them with enough resolution for long enough to mimic the evolution of the universe. Okay, so this is how galaxies form, like Schrödinger's cat. Okay. Tiny fluctuations, quantum fluctuations, get blown up by gravity. Okay, so with this, this brings us a full circle. This is that afterglow image, afterglow from the Big Bang. Those tiny spots, hot spots and cold spots, are the fluctuations in the early universe. You take a hot spot, that's the up fluctuation that becomes a mini galaxy, infant galaxy, that then collide with other galaxies to become a bigger galaxy. Within it, there are stars. Some of those stars explode at the end of their lives. They produce the elements out of which stars and new stars and planets are formed. There are wonderful complex molecules on the surfaces of planets and wonderful living things. Okay, so this is my story. This is actually my son is accompanied by my daughter in this picture. This is my story, and I'm sticking to it. Okay, so we are at 8:15 or 9:15. Sorry, we're a little 75 minutes from the 8 o'clock start. I want to spare the rest of the time for Q&A. Oh, thank you. Thanks, Raj.
I have a quick question. When you mentioned that in the last 10 to 20 years, the Andromeda Galaxy has been, we've been able to resize it to what it actually is versus what we thought. Mm-hmm. Similarly, although we're in the Milky Way galaxy, have we had any thoughts as to providing a more updated number? It's not 100 to 110,000 light years, but it's something else.
Yeah, absolutely. Like no, there is a very good update like that. In fact, one of my PhD students, he defended his thesis topic earlier today, and this is exactly the subject of his thesis. He's finding the most distant stars in the Milky Way, stars for which we know precise distances, and the ones he's found are about 40 times further away from the center of the Milky Way than our solar system. So we are 25,000 light years from the center of the Milky Way. The solar system is, you multiply by 40, you get 1 million. So these things are about 1 million light years away. And so the diameter of our Milky Way is something like 2 million. Now, Andromeda is about 2.5 million light years away. So if our galaxy extends 1 million in all directions, including towards Andromeda, there's very little space left. Andromeda is a bigger galaxy, probably. And this is only how far out we've mapped it, mind you. We haven't seen a sharp cutoff yet in either galaxy.
Then theoretically, aren't the two galaxies already touching?
They are.
They're very outskirts.
Yeah. And what that means is, in the very outskirts, stars are there's a tug of war for stars, for particular stars, and a star may go from the gravitational influence of one to the gravitational influence of the other, because it depends on distance. And if the star is moving, right now it may be feeling a stronger pull from the Milky Way than Andromeda, but if it's moving fast enough, it may actually get to a point where it's feeling a stronger tug from Andromeda than from us. So there are stars in that twilight zone between galaxies.
What about the voids, like the Botez void?
Oh yeah, so those are examples where shortly after the Big Bang, there were down fluctuations in the energy density of the universe. So what happens is, if you have a region of space where there's less density than average, it starts to empty out over time. The rich get richer and the poor get poorer in under the influence of gravity, just like human society. So what happens, I'll explain the physics of this very simply. If you have a perfectly uniform density of material, every particle feels an equal pull in all directions because there's equal density all around. If a particle is on the edge of a void, for some reason, there's an underdensity and a particle finds itself on the edge of that, it's going to be pulled harder on all sides except towards the void. So it tends to move away from that void, making that void even more extreme. And the opposite happens if you've got an overdensity. All directions pull it, but it feels an extra pull towards the direction that has extra material and it migrates towards it. So the rich get richer and the poor get poorer under gravity. So the Botez void, we think, formed because it started out as a quantum fluctuation that happened to be down compared to the local group where the Milky Way, Andromeda, Triangulum, etc. sit. That happened to be an up fluctuation. Yeah, happened to be, I say, but on the other hand, if we are saying we needed to be in a galaxy, it's pretty inevitable that we would end up looking at the universe from a perspective where we started out as high density things, within high density things that became galaxies.
Professor, this is Vasant. A couple of times along the way, you talked about the supernova explosion being moderated by the amount of dark matter in a galaxy, or galaxy collisions being moderated by the dark matter in a galaxy. You didn't actually mention the nature of that dark matter, or how are you detecting that?
Yeah, sure. So the way dark matter was first found was by Vera Rubin, and she found it in galaxies. She found that galaxies are just spinning way too fast than they should. But what I mean by that is if you just count up how much light there is in a galaxy, like say like the Milky Way or Andromeda, you can count up how many stars there are. You can make an educated guess for the stars you see their collective light, but you can account for their mass, right? If you do that, you can predict how much gravity should be pulling on every object. And the Andromeda Galaxy should have been spinning at 80 kilometers per second, 80. It's spinning at 250. It's not a subtle effect. So Vera found that every galaxy that she looked at was spinning something like 3 to 2.5, 3, 4 times faster than it should, based on how much starlight she saw in it. So the evidence of dark matter is right there. Galaxies are spinning faster than they should. And so when I say it's moderated by dark matter, the gravity of stars is minuscule. It's about 10% of the overall gravity of the galaxy. So when galaxies collide, it's really the dark matter talking. Or when we're talking about the supernova being reined in by the gravity of the galaxy, it's a dark matter that's doing the heavy lifting.
All right. Now, what's the nature of this? I know we discussed yesterday. What's the actual nature?
We don't know. This is one of the wonderful things. This is what's going to keep me off the streets for a long time, right? Because we don't know. We just don't know what the dark matter is made of. We don't think it's made of black holes. We don't think it's made of dead stars. We think it's made of small particles. But there are physicists who are looking for these, astronomers who are looking for these. We don't know exactly what the dark matter is made of. We don't know what dark energy is made of. They are truly secrets of the universe. And it's not like people know and they're hiding these secrets. No one knows. They're ruling out different things based on evidence, based on predictions of certain models. But we still don't know what the dark matter is. We don't know what dark energy is. We understand black holes somewhat better. But so I can keep giving this talk for a long time.
How did Vera Wang use light to determine how fast the galaxies are rotating?
So Vera Rubin, what she did was she took spectra of the ionized gas in Andromeda and other galaxies, ionized gas. So she looked at ions like hydrogen, nitrogen, oxygen, etc. And these ions emit light at very specific wavelengths, emission lines. And so you can use that to measure, if you have a rotating frisbee, one side is coming towards you, one side is going away from you. She measured that. She measured that and figured out how fast things were rotating. That technique had been around for a long time, but people had never tried to put that math together. How fast should it be spinning versus how fast is it spinning? So Vera got to a point where she could, when you look at the inner parts of galaxies, they're not spinning that fast. And so there was no evidence for dark matter. But when she went further and further and further out, you were running out of material. There's no more matter, but galaxies are still spinning fast. That means there's something unseen whose gravity is continuing to dominate at these large radii. So Vera needed sensitive instrumentation. And I had the good fortune, I was working on how fast galaxies spin when I started grad school. So I met her at several conferences. She was a remarkably kind person. And one of my Santa Cruz colleagues was mentored by her. So I hear lots of stories of Vera and the good fortune of knowing her. No, she didn't believe herself when she first made this discovery. She called it missing matter because it looked like the matter was there, but it wasn't actually there, is how she thought. But it's not really missing. What's missing is not the matter. What's missing is the light it should be putting out. The matter is not missing.
Early on, you mentioned that our sun can produce elements up to 7 or 8, and yet these heavier elements exist because of the dust cloud from which the sun formed.
Mm-hmm.
Are we able to determine whether our sun is a subsequent daughter star or a granddaughter star or a great-granddaughter, anything like that?
That's a great question, Avanish. It's not, the reason it's not finite generations like that is the sun formed out of a nebula. The nebula is being rained on every time a star explodes. Okay.
Right. Okay.
And literally there could be an explosion quite far away, but if the ejected material goes far enough, a little bit will land here. It's very analogous to, if you think about the soil out of which a plant grows, those particles can be blown by the wind for miles. It can, they could have, if those particles were being produced by, in this case, the particles are being produced, the particles of our atoms are being produced by different stars. It's not like these stars all explode at once, and that's one generation. Different stars explode at different times. So we can tell that the sun, the nebula out of which the sun formed, had quite a lot of enrichment. The sun was already born with a lot of elements. The sun is unusually rich in heavy elements compared to other stars around us. The sun is not a median, not an average object in terms of chemical composition.
Okay. Great. That was one of the clearest answers I've heard on that for that topic. Thanks.
Thank you.
I have a question about gravity waves. I've previously thought of gravity waves in the same way I thought of light waves, but the way you said something today made me think slightly differently, which is it was detected as a point in time due to a collision of neutron stars. So is the right way to think about it as the result of an explosion where there's a sudden extra release of energy in the form of light and gravity, space-time distortions? How should we think of gravity waves?
Gravity waves should not be thought of as a burst of electromagnetic energy. When neutron stars merge, the fabric of space-time goes through this little quake. When black holes merge, they go through the same thing. So that quake, that sudden, that ringing when they finally merge, that's what produces the gravity waves. With neutron stars, other things go on as well. So there's an explosion, and that's what produces the light. But gravity waves in their purest form are not accompanied by electromagnetic radiation. They are just ringing of space and time, periodic ringing of space and time. You need a periodic phenomenon, like one thing orbit another. You need something called a quadrupole moment in general relativity. You can't get it with a dipole. It's a quadrupole moment will produce it. But another way of saying this is there are not positive and negative charges in gravity. There's only charges of one sign. When you think about gravitational attraction. In electrical attraction, there are opposite charges. In magnetic, there are opposite polarities. Gravity doesn't have that. So you need a quadrupole moment to get gravity waves. But you can get that from a pair of objects going around each other. So the energy comes from E equals mc squared. If you start with two masses, m1 and m2, when they merge, the resulting mass is less than m1 plus m2. And that deficit is what's been converted. You multiply that by c squared. That's what's been converted to the energy of gravity waves. That's what the gravity waves are taking away from the system.
Now, Professor, in that diagram you had of the cosmic soup and from the Big Bang to today, it went back all the way to, I think, 10 to the minus 37 seconds.
Right.
Now, I recall that Planck time is 10 to the minus 43 seconds.
This one, right?
And so far, they just have not been able to go beyond that.
That's right.
Do you foresee any eventual progress, or is that just seen to be an insurmountable limit?
Seems like an insurmountable limit to me. Here's the other thing. We can't see anywhere close to Planck time directly. The furthest we can actually see photons from is about 380,000 years after the Big Bang. So somewhere where my cursor is.
Okay.
Beyond that, the universe was opaque. So light couldn't travel freely. Photons couldn't travel freely through the universe. So this afterglow from the Big Bang we see left the universe when it was 380,000 years old. So forget about 1 second or 10 to the minus 40. We can't see beyond 380,000 seconds after the 380,000 years after the Big Bang. Anything earlier than that, we can't see directly. We can infer indirectly through physics. That's how people talk about Planck time, is through the physics of what, sort of indirectly though.
That's what I meant. They can't even infer indirectly beyond Planck time right now.
No, that's sort of it would, my understanding is it would violate the uncertainty principle if you tried to ask questions of finer detail. Because quantum mechanics is this cruel subject that says you can't ask questions of too much detail when you get to small enough scales. And just like you have momentum and position coupled through the uncertainty principle, energy and time are similarly coupled through the uncertainty principle. So when you're getting close enough to the Big Bang, because delta T gets very small, the uncertainty in energy is so large that you can't, things are very fuzzy from an energetic standpoint. By fuzzy, I mean indeterminate.
Thank you very much. Any other questions?
Yes, this is Brian Smith. I have one. My question is, I understand that matter seems to be created spontaneously in a vacuum, from what I understand. Is that correct?
It can be. There's this notion of a false vacuum. This is related to Hawking radiation and false vacuum. Matter, generally matter can be created from energy. Okay, so E equals mc squared means you can take energy and you can take two photons and you can create you can make those photons disappear and create two particles. You can create matter from energy. Can you create particles from nothing? And the answer is yes, you can, because when you say nothing, a pure vacuum, if you said something is a pure vacuum, you're violating the uncertainty principle, because you're specifying exactly what the energy of that space is at every instant of time. So that leads to this notion of false vacuums. That is, what people traditionally thought of as a vacuum is allowed to fluctuate up and down in energy in order to satisfy the uncertainty principle. And when it fluctuates up, it can produce particles. I don't know if I'm answering your question.
Yes, you did. You answered it perfectly. So in the universe, matter is being created and annihilated all the time.
That's right.
So wouldn't that be evidence of dark energy?
Not necessarily. Not necessarily dark. I mean, that would be evidence of energy, and that energy is often referred to as, the energy of the false vacuum. Dark energy is often referred to as vacuum energy. That is, it's energy that does not require the presence of matter. There are close analogies with the notion of a false vacuum and dark energy. But all we can, from an experimental standpoint, all we can see is something is pushing galaxies apart. Gravity is trying to pull them together. Something is pushing them apart faster than dark matter can pull them together. We don't know what that entity is. We don't understand how it operates at a microscopic level. And
Well, I was gonna say, isn't that a possibility that this matter creation and destruction all the time is creating an overpressure that's pushing these galaxies apart?
You know, the thing about the fluctuations of vacuum is it should be symmetric around zero.
It should be.
Yeah.
But it's not, right?
But yeah, dark energy is telling us that there's a finite amount, that is the mean energy is not zero. There's a, it's a non-zero energy associated with a vacuum. In this sense, it's different from the vacuum energy phenomenon. Vacuum energy, the whole notion of a false vacuum, I shouldn't say vacuum energy, the notion of a false vacuum where particles can just spontaneously appear from a vacuum is fluctuations about zero. And dark energy requires that there be a finite amount of energy. The mean cannot be zero.
Okay. So I know this, I know you're not going to know the answer to this because no one does yet. And that is, what is gravity?
Yeah, so Einstein tells us to think about gravity as not as a force, but as the distortion of space-time by any object that has mass. Now, we don't have a complete theory of how gravity behaves on tiny particle scales, on quantum scale. We don't have a complete theory of quantum gravity. This is something that string theorists are trying to work towards. This is something that Einstein had dreamed about, but we don't have a theory that unifies quantum mechanics and gravity. We don't have that yet.
Okay. I'll stop there because I don't know any more than that. And I want to thank you for your time, Professor.
You're most welcome. Thank you. Thank you, Brian.
And good presentation, by the way.
Thank you.
Thank you. Thank you.
I would say that's 9:36 p.m. Unless there are any last questions, I would call for a round of applause for our eminent speaker.
Thank you.
Was done an outstanding job. You can react on
Yes.
Zoom, of course.
Thank you. Thank you very much.
This was a pleasure, Professor. Thank you so much.
You're most welcome. Thank you. Thank you.
And hopefully in the future you can come out and speak to us in person.
I will do that.
Yeah, thank you for taking your time out to come to our club.
Oh, I would love that. I should say that astronomy is my plan B. I really wanted to be an artist, and one of my big regrets in life is I chose art as a hobby and science as a profession. But I finally got my break a few weeks ago where I'm going to get a solo art show at Santa Clara. So I do pencil drawings. 6 of those pencil drawings will be on show. So that's made me more happy than anything that's ever happened to me in astronomy, which really reminds me that this is my plan B. Art was my plan A. So next time I come out, maybe I'll talk about art. Just kidding.
That'd be the Sacramento Valley Art Association, and
that's right.
they meet on another night.
You would love the Crocker Museum of Art here in downtown Sacramento then.
Yeah, I think I have been there actually. Yeah, this is going to happen in a museum in Santa Clara called the Triton Museum. Astronomical name for it, Triton. So thank you. Thank you all. I really appreciate your taking time on a Friday night like this to listen to tall tales about the universe.
Yes, we have an audience member chime in that she'd be very intrigued to see your artistic renditions of astronomical objects or phenomena.
One of my drawings has some astronomical things. Most of the time, those two things are very separate for me. I mean, the techniques are similar, very detailed, and there's creativity and mystery. You start with something, you end somewhere else. But I generally don't draw astronomically themed things. But
our audience member clarified that she's the one who actually wants to make that kind of art.
Oh, wonderful, wonderful, wonderful. Where are you seeing this? I'm not seeing this on the chat.
On the chat room.
Oh, maybe I'm missing it. Okay. All right. Thank you so much. And Raj, thank you for contacting me.
Of course, Professor.
It's all worked out. Thanks.
Yeah.
All right.
Thank you so much. Very, very interesting talk.
Thank you.
All right, we'll end the recording now.